Yeah, ladies and gentlemen, I want to give you a short update on ngspice development and have some application which I was dealing in the recent past is electrothermal simulation. Well, my name is Holger Vogt. I'm from University of Duisburg-Essen in Duisburg in Germany, and I'm also with the Fraunhofer Institute on microelectronic circuits and systems. Okay, yeah, just to wrap up, ngspice, what is it? It's a circuit simulator. It shows the equations of electronic circuits, and these electronic circuits may be made of passive and active devices. And we want to solve the equations for time-varying currents and voltages. And it's, well, its name says it, it's the open source successor of the venerable SPICE-3 from Berkeley. Well, what do we have? In fact, we have a circuit on the far left, simple circuit here in CMOS inverter. But this is not the input SPICE typically has because it's a command line input. And we use this thing in the middle, just a list, a net list, which gives us the devices and the connections and some simulation commands. And the output is on the right. This is a graphical output of, for example, where voltages versus time. You see some pulse waveforms, input and output of an inverter. Okay, so ngspice has two major application areas. The one is PCB design support. Well, typically here circuits are made of a mix of ICs and discrete components. And there you have the requirement, well, have a comfortable user interface. Okay, you have seen ngspice is a command line, so this is not that comfortable. So we rely on others. We rely on KiCad and we rely on some other parties to offer, for example, schematic capture. And when we do these circuit simulations, we have to be compatible to some well-known software tools like pSpice and LTSpice. This is mostly concerning the device models we are using. On the other hand, we have the capability of doing IC design support. Mostly today, ICs are made of MOS devices, and you have many of them. And you would have some parasitic devices as well, of course, resistors and capacitors that are included in your circuit. There we need compatibility to existing device models, Berkeley models, BSM3 and 4, and maybe BSM bulk and others. And we have to have large circuit capability, a few thousands or even 10,000 of transistors. Therefore, we need a certain simulation speed. And we should be compatible to some process development kits that are offered by the foundries. So you get their device models from the foundry. And typical software used there is HSpice, so we try to be HSpice PTK compatible. And in red and down, you see some software using ngspice and supporting ngspice, both on the PCB design support side and also on the IC design support side. Okay, so what is the status or what we are doing right now? So we are working towards ngspice 32. Should be available hopefully in March. Well, as you see from the things we are doing there is no revolution going on. It's a lot of evolutionary development moving on. Improved graphics for the output, both on Windows and both on Linux. We want to add Unicode support, that we use UTF-8. Strings and white charge strings on Windows, and that we can use Korean and Chinese and Russian and other languages or texts for plots, node names, file names, directory names. And we have compared to the last ngspice issue, a revised model for PowerMOS devices. An efficient model, this is this VDMOS model, and this now includes self-heating. And I will talk about that in a minute. Well, in addition, of course, we have a lot of enhancement of robustness, bug fixes, improved error handling. So if there is an error, get better error messages, major code cleanup is in fact going on, and therefore the interconnection to users, maybe on the KiCad side, maybe direct users of ngspice are important to react, and we are relatively fast. Sometimes bugs are fixed within 1 day if required. Okay, just some impressions. Well, how to input things into ngspice. Now, for example, we are KiCad. Well, a power amplifier schematic here, and you can directly get the netlist out of KiCad into ngspice and either use the internal KiCad ngspice version, or you can offload it to external KiCad. Well, and concerning IC work, there is a relatively new thing called XChem, and integration work is going on there also for IC work. Well, and the output is lots of different graphs. It's GNU plot output. It's the internal ngspice plotting capability. We can write PostScript files, and we can, of course, use the KiCad integrated output. Okay, so I have been saying that I want to go a little bit into one special application area. This is electrothermal simulation. Starting, well, with if you are familiar with MOS devices, you see these output characteristics of an MOS device. X-axis is the drain voltage, Y-axis is the current. And what is happening? Well, you increase the drain voltage and the current is decreasing somehow. So this is strange, yeah? Do we have negative resistance in our MOS device? No, it's a very simple thing. This device heats up. And because we have, of course, we have some power dissipation. You see 10 volts and 2 amps, 20 watt power dissipation in the device heats up. And so the electrical characteristics of this device is changing. Especially here, the mobility of the charge carriers is decreasing, and so the current decreases with increasing temperature, simply. And the temperature increases because the power, the dissipated power might increase. Yeah, and so how can we do this? How can we model this? And this is the idea we want to, we have integrated recently into our devices. Yeah?
You're keeping the gate voltage constant?
No, the gate voltage is stepwise. Okay, so the question was, do I keep the gate voltage constant? No, I don't. This is stepwise increasing in gate voltage here. Yeah, so the lowest graph is the lowest gate voltage, and it's just raising up. Yeah, so this is about electrothermal modeling, and what is it? Yeah, we make use of the equivalence of thermal circuits and electronic circuits. Yeah, we translate thermals into electrical circuits, and then we run both circuit parts in ngspice. So electrical power dissipation generates heat. Heat has some restricted flow path, and so it rises to the temperature of the device. Temperature changes some device characteristics, and so we have this closed loop. This has to be integrated and, well, deserves special device models that can react to this. And in the table you see, okay, the equivalence of electrical and thermal terms like the heat capacitance, the capability of a material to store heat, similar as electrical capacitance. Or we have the conductance, the thermal conductance. The heat flow is restricted somehow. It's the same or equivalent as a resistor for the electrical current. Yeah, and so because we can do electronic and thermal circuits at the same time, well, we can simulate them at the same time. Here you see just another power amplifier made in KiCad schema for generating the ngspice netlist. And you see the MOS devices, and these MOS devices, the power devices on the right, well, on here, they're a little bit special because they don't have only 3 pins, but they have 5 pins. And they have 3 electrical and 2 thermal pins. Thermal pin is the junction temperature, and is the outer case temperature. Yeah, so this is the interconnection between the electronic and the thermal circuitry. And on the right, you see, well, this is our thermal circuit. And in fact, this is a the electrical equivalent of a heat sink. You have a small resistor coming in here. This is how the transistor is put onto the heat sink with some glue or whatever, had a certain thermal resistance. And then we have a capacitor because of the mass of the heat sink that has a thermal capacitance. And you have a resistor, the thermal resistance of this heat sink. And then we have a voltage source. This is the outside temperature, 42 degrees here. And then you can do this simulation, because it's now all electrical devices. And of course, ngspice can do this in a complete single fashion. Well, on the left, you don't see much about these temperatures. It's just the input voltage and the output voltage. So the amplifier is amplifying. This is great. And on the right, you see simulation for about 10 seconds on the x-axis. And the output, well, here it's named voltage, but in fact, it's the temperature you see here. You just see the temperature of this transistor on its heat sink is rising. Well, and we have the outside case temperature here, and we have the junction temperature here. And typically, junction temperature is specified in the specification sheet to be not be beyond a certain maximum. And this can be simulated here easily now with a co-simulation of electrical and thermal circuits. Okay, and you can do other things. This is a resistor, a simple resistor, which has a negative temperature coefficient. That means the temperature rises, and the resistance decreases. And we put a voltage on, and we simulate versus time. And we see where the temperature is rising and rising and rising. And at a certain point, the thing breaks down. The temperature goes up beyond all bounds. And this is simply a thermal runaway. Yeah? And so you can simulate the limits of your system capability before it starts to explode, let's say. Okay, so to summarize, well, ngspice hopefully will be available in March this year with several new features, many bug fixes, Unicode compatibility, enhanced Monte Carlo simulation capability. I didn't talk about this here today, but this is another thing of interest, especially for the IC designers. And we have these electrothermal models of power devices integrated. And even then, well, we just think about what will we do next for ngspice 33. Thank you.
The simulation is as good as the models are. Where do you get the thermal capacitance of your transistors, etc.?
Yes, this is. The question is, where do I get the modeling data? Because the models are as good as well the input data are. Yes, one has to look a little bit into detail. So for the transistor itself, it's just so judgment. How much copper is in, how much plastic is in, and then you have weight, and then you have a thermal capacitance of the material, and then you can calculate the thermal capacitance. For a heat sink, well, the heat sink manufacturer will deliver these things to you.
Is there a native way to do like these thermal calculations in KiCad, or do you have to kind of trick it? Like in the example, it was thinking that it was doing computations on voltage and current, and then you kind of tricked it because it was doing things on temperature. Do you have to do that, or is there a native temperature way in KiCad?
No. Yeah, the question was, is there a native way of doing electrothermal simulation in KiCad, especially because on the graph it was voltage, and in fact it was temperature? Not yet. It's just a matter of this interface between KiCad and ngspice. So ngspice, in fact, does calculate voltages. And then you could tell, of course, the graph, the output graph, it's not a voltage, it's a temperature. Because the equivalence is clear, and the equations, the relationship between these two is clear. And so ngspice calculates voltage, but in fact it's the temperature. And the graph should show temperature, yes. Within ngspice directly, you can just tell it, this is not a voltage, this is a temperature.
Yes, please.
So I'm not very satisfied with the look and feel of the cadence virtuoso simulation tools. Can I somehow take my cadence IC models or my circuitry and export it and use ngspice for that?
The question is, can one take a cadence simulation environment, the data, and put them into ngspice and do simulation? Yes, there has been some guy doing a translator that takes the cadence spectra input thing and translate it into the ngspice netlist. And the models, of course, you have to select. ngspice had a certain number of models available, and if these are the same as cadence, and well, BSIM3 for older processes, BSIM4 for newer processes, then you can do that.
Maybe a bit of an outdated question, but you mentioned at the beginning of the presentation compatibility with LTSpice, and some time ago when I was downloading models from the LT or another device website, I would have trouble simulating all the polynomial functions. Is now compatibility with LTSpice fully addressed, or are there still some functions that are missing in the compatibility of ngspice with LTSpice models?
Oh, the question was compatibility between LTSpice and ngspice, and especially polynomial functions. Well, there is a polynomial function capability in ngspice, as has been in the old Spice 2. It's the same feature, same function. This is working. Well, if you say if it's fully compatible, well, we are never fully compatible. Main reason is we don't know what LTSpice has in. Yeah, so we don't know the equations of LTSpice. So we can just figure out should be similar, and this is what we are doing, and this is continuously improving. Yeah.
One more question? Oh, sorry. Yes, please, in the middle.
Okay.
Raise up high.
What is the licensing situation of the models?
The question is, what is the licensing situation of the models? Good question. Well, the model development is mostly nowadays done proprietary. These well, companies pay for this model development, and models are publicized some with some delay, maybe a year or two, also on the open world. And there is, I think, model developers have, and their parent, the companies have agreed upon a so-called, I don't know the abbreviation, educational license too. And now they offer these models under this specific license. This is a sort of open source license. I just have to clarify if it is Debian compatible, because these are the very strict people will do that. And if this is difficult, well, then we have two distribution channels. We have ngspice, and we have another download for, especially for Debian people, and we have another download on the models, and you can link it together. So both are open source, but maybe not the ultimate, most newest model is available right now. It's take a year or two.
Thank you.
Okay, thank you.
Very nice. Okay. So it's